Ladies and gentlemen, this is Mukhtar bin Abid from Center of Solar Energy Research and Studies in Libya. We'll talk today about the simulation and evaluation of the solar energy system in the public building in city of Tripoli. The paper deals with the mosque sector as an example. The talk will be divided into the introduction and the common step of data collection. Then we'll go through the first section of the research, which is the solar thermal system. We'll talk about the load estimation and system modeling and simulation. Then we'll take the second section, the solar PV system. We'll talk about the load estimation and system component sizing. Then we'll finish by the conclusion and the recommendations. First of all, the solar energy drivers in Libya is its location. Simply, it's its location. It's the daily average of solar radiation on the horizontal plane is 7.1 kilowatt hours per meter square per day in the coastal region, where there is some duration greater than 3,500 hours per year. Actually, the shortage in electricity and fuel that happens uh, in the recent years uh, promotes the cost of energy and makes the public realize the importance of the solar energy. So now let's talk about the problem statement. In Libya, we have more than 5,000 mosques, approximately 8,000 to 9,000 electric water heaters. The average of them, or the most of them, are 80 liters and with 1500 to 2000 watts for each. Moreover, inefficient construction for the buildings uh, leads to high heat losses because it's without any insulation that requires large amount of cooling and heating. The electrical energy demand could reach to nearly 200 kilowatts for some mosques, with lighting demand of 11 kilowatts. All that, all of that made the Authority of Islamic Affairs to require a study for 10 mosques in the central Tripoli in order to create this problem. The first step is data collection. It's done by the questionnaire filled by researchers and mosque servants. The data was about the number of the hot water consumers and the worshippers, the hot water consumption during ablution, the building orientation and the shading from the surrounding buildings, the water source and its quality, the lighting loads, the air conditioning loads, and the estimating of available area of the installations, which is normally on the top of the building, on the roof. In this slide here, we can see the questionnaire results and the data collected by the questionnaire, and the results the estimations relied on the questionnaire data. The water consumptions and the fundamental estimation of the solid water heater number estimation, as we see in the right. We can pick some numbers here in the Mosque number 4, you can see that the water consumption was 1,612 liters. The pre-estimated number of the solar water heaters was 7, and the location was partly shaded along the year. Here is the most interesting part that I like from the shading analysis results. On the left, the sun path diagram, where it represents the sun movement along the year, and the green bars represents the shadow. As we see here is the bad case for the winter. The location can't get any solar radiation in the winter, while it's not good for the saltwater heaters, but the PV systems could get some radiation in the other parts of the year. On the right, the table represents the directions and dimensions of distance of the surrounding buildings. So now let's go through the first section of the study, the solar thermal water heaters. Well, first, the thermocycle system is widely used due to its low price. It is easy to install, and the fluid is naturally circulated, so no pumps needed. The load estimation is done accordingly to the required hot water loads. However, the installation location is restricted by the consuming place. It should be installed at the top of the consuming place. We have dushing rooms here in this case because we don't want to lose a lot of heat by the piping system. In contrast, the PV systems are relatively flexible, more flexible. Now let's look again to the questionnaire results, and let's look more to the water consumption by liters that extracted from the data, and how much solar water heaters estimated for each location, and the notes that written from the visitors about the location and shading. TSOL is a program for design and simulating solar heating applications. It does shading analysis for specific size. It's used for this study where the Solar Energy Center Libya in Tripoli, Libya owns a license for it. In the next slide, we can see the results of the TSOL program simulation, where the green bar represents the total load, and the blue bar represents what offered by the solar water heater. The red line, the red bar, represents the what offered by the auxiliary system. So the behavior of the solar water heater reveals that the one solar water heater is not enough for to fulfill the hot water needs. Next, we can see the same simulation results. They are for 21st
For many mosques,
December,
like the previous
and
results,
the worst case designed based on the
large
21st
amount
of
of
December
hot water is
as a design
required.
day.
So we can
It
see
shows that
we can see another scenario.
only
If we
one
can go through the
system is not enough
pump
for
systems
the forced circulation
for the load.
systems, which produces higher thermal power, as we see here. For some locations that the roof is not fully shaded, we can get the forced circulation system, and we can see the results that the annual behavior here in this slide. It seems that it can fulfill the needs of the system. We can fulfill the needs of the site, of the load and hot water demand for all the year. And this chart for the same system is for the 21st of December. As we see, we can fulfill the needs of the hot water, and this system is consisting 15 square meters of solar collector. The selected system. The selected solar collectors are Vitosol 100, Viessmann, which is Viessmann company, 2,000 liter tank with auxiliary fuel powered system. With this equipment, it can provide 60% of the annual solar share and 70% of the winter daily solar share, which is should be good, and high solar share. So let's go through the solar PV system design. Here we can see the steps that is followed by the designers. You can see as a result of questionnaire and data collected by questionnaire, the collaboration of the mosque servants, the electrical loads and appliances, electrical loads and their operation duration. It's found that the air conditioning load is too high, so it is omitted from the plan. It's omitted from the plan. The air conditioning, as we talked about that later previously, it is because of the bad material, the uninsulated, no insulation is installed in the buildings, and that's why the air conditioning and heating loads are very high. So the AC load is omitted from the plan. Even after the dropping AC loads, we can find that the electric loads still high. So what's the plan B? So due to the high electrical loads, it is decided to install PV standalone systems for the critical loads, only the critical loads. As we see in this table, we can see that the loads are too high. The average daily electrical loads per month is in kilowatt hours. It's too high, as we see. It could reach 40 kilowatt hours per day. Then what's the critical loads? The suggested critical loads are LED lights, 15 LED lights with maximum power of 18 watts each. That could offer nearly 30,000 lumens, and only 1 horsepower pump for water supply. For the BA system, 600 watts for two speakers, one internal and one external. Then finally two water coolers, about 220 watts for each at maximum. The results of the design process is illustrated here in this table. The PV system and the inverter, the batteries. SAM software is used to simulate the design system. Here in the chart we can see the load by the blue line and the production, the electricity production produced by PV in orange bars by kilowatt hours per day, the average daily per month. In conclusion, the mosques in this study are located in crowded sites with high demand, high water heating demand, and the most of the mosques are built in shadow of the surrounding buildings because they are in the city center. So various solar thermosiphon systems are required, and sometimes it's better to get pumped systems instead of thermosiphon systems. And in some cases, no solar water heaters could be installed. The optimum location of those mosques contains the ablution sites in the south of the building. It's better to be in the south in order not to be shaded by the building of the mosque itself. In spite of the high electrical loads, it is still available to employ PV standalone system for the critical loads. And that's the conclusion. Finally, the authors recommend the installation of forced circulation systems in the case of high hot water demand and available unshaded area. At the same time, the installation of thermosiphon systems in the suburbs and countryside mosques because of the wide area, no shade, no high loads. At the same time, we recommend the government to support the solar energy devices where the conventional power sources are subsidized in Libya. That's all for competition and to encourage the people to go through them. Hey, finally, thank you for listening. And if there are any questions, I'll be happy, and the other authors will be happy to answer them.